Hello, everyone. Well, thanks so much for coming in such a rainy, cloudy, stormy day. So my pleasure, to have Barak with us today, giving a seminar. Let me see. So Barak did his undergrad and also PhD at the Hebrew University of Jerusalem in the chemistry department on molecular dynamics, I guess, mix of quantum and classical. And then he did a postdoc in ETH Zurich with Michel Parinello, again, continuing on quantum dynamics method development. And since
2021.
Okay, 2021, he has been an assistant professor at the Tel Aviv University, where I also came from. And again, they're continuing with a mix of quantum method development, quantum simulations, and classical, and we will hear about this mix today. So please, welcome.
Thank you, Dvira. Thank you, everyone. So I'll start by saying, well, thanks, Dvira, for having me here. It's my first time in Canada, first time in Toronto. I'm enjoying your lovely weather, right? But honestly, I'm very happy to be here. If anything's better than the 36 centigrade at Tel Aviv right now. So this is even a thunderstorm. Wait, but I think this is blocking the view. So let me get this out of the way. Now it's better, right? Okay. So today I'll tell you about our recent work trying to develop new algorithms for molecular dynamics simulations to do two things. The first is to try to get them to be able to describe long timescales, much longer than they could do using the standard approach. And the other thing is trying to have the cake and eat it too, trying to use classical simulations, but to obtain quantum expectation values from them. So those will be the two parts of my talk today. But if you will allow me, I'll start with one slide of PR, acknowledging the people who actually did the work. So I've established my group at Tel Aviv about 3.5 years ago. And when I started tenure track, people told me that you start to enjoy it in your third year. So I can confirm that I'm enjoying myself. We've formed a stable nucleus of a group. And the people who actually did the work that I'll tell you about today are two. The first part of my talk will be the work of my postdoc, Yotam, who's here. And the second part of my talk, this will be with the quantum statistics and classical simulations. The second part of my talk that will involve the long timescale sampling and molecular dynamics will be the work of Ophir Blumer, who's my PhD student. And all the work is funded by the Israel Science Foundation, the United States Israel Binational Science Foundation, and the Pazi Foundation. So the main workhorse that we use in the group is molecular dynamics simulation. So this is, I didn't know if would be more of a chemistry or a physics seminar. So who of you knows what molecular dynamics is? Who doesn't know what molecular dynamics is then? Okay, so let me make sure that everyone knows what it is. Molecular dynamics is just conceptually very simple. You take a collection of particles, it could be your atoms, it could be your molecules, it could be as many molecules as you have in a big liquid droplet or a piece of a solid. We're talking even about millions of atoms, right? Not Avogadro number of particles, but even millions of thousands and millions of atoms. You put them in a box in the computer. You define what the interactions that they feel, what the forces that they exert on each other, and then you numerically solve Hamilton's equations of motion. That's what you do in molecular dynamics simulations, right? Conceptually very simple. And they give really wonderful insight into chemical, biological, and physical phenomena. They generate this movie that you can follow in time, how every atom in your system develops as a function of time, okay? So they're wonderful. And why am I telling you about them? Because I think that they still have two very serious limitations that we're trying to overcome. The first limitation is, because you want to make this movie where you see every atom in a solid or in liquid or in a complex interface of phases evolve in time, you have to use a frame rate for your movie that's very short, right? The time step for the dynamic propagation has to be very small, smaller than the fastest motions in your system. With molecular and atomic systems, that's usually the vibrations, right? That makes the time step on the order of a femtosecond or a fraction of a femtosecond. That means that the total duration, since we're numerically solving the equations of motion, the total duration we can look at is rather limited. More or less, it's limited to about a microsecond, even today. And many processes takes place on much slower timescales. So if you want to do simulations for timescales that are longer than microseconds, you simply, even today, it's very hard to do using standard molecular dynamics simulations. So the other part is maybe, more obvious, and that is that by doing classical equations of motions, you neglect all quantum mechanical effects. And that while that might work for, a bunch of systems, if you want to describe quantum materials and stuff like that, that's not going to work at all. The other alternative of solving the Schrodinger equation for liquids or solids is extremely complicated, so you can't do that as well. So the question is whether you can have the cake and eat it too, whether you can do classical simulations but include important quantum mechanical effects. That's the other side. And the way I see the vision of my group is try to develop algorithms to overcome both of these problems. Now, clearly, we're not the only group in the world doing this. There are some excellent groups here doing just that. But I'll try to focus exactly on what I think is our unique approach to either one of these problems. And let me start off by this side, by how to include quantum effects at a classical cost in molecular dynamics simulations. And I'll tell you about a work that started when I was a postdoc with Michele Parinello at ETH. I was working there with Valerio and Chang Wu, who were members of the group. But since I joined Tel Aviv, the work really has been picked up by my postdoc Yotam. And it involves in doing what we call path integral molecular dynamics simulations, so classical simulations that include quantum effects. In particular, how to include one of the most fundamental quantum effects there is, the fact that quantum particles are either bosons or fermions in this classical simulation frame. Okay. So what is path integral molecular dynamics? So most of you have heard about molecular dynamics simulations. How many of you have heard about path integral molecular dynamics simulations? Many less, right? Much fewer people. So in brief, this is all you need to know about it. It starts with a correspondence principle that first time I've heard about it blew my mind, that Feynman told us many years ago. And it says that for every quantum system, I'm going to give you an example of a single particle in a trap just because it's easy, but it's true for every quantum system. You can map it into a larger and extended classical system by, instead of, in this case, taking one quantum particle, putting p copies of that particle and connecting them with harmonic springs onto a ring polymer, okay? And the frequency of the springs is proportional to the temperature. And if you sample the classical partition function of this ring polymer system, you actually can extract quantum thermal expectation values for the original system you're interested in. Now, if you've never heard about this, you might, don't understand why this is true. So I'll give you the physical intuition. And the physical intuition comes from the fact that these springs, they have zero rest distance and they have a frequency that is proportional to the temperature. So when the temperature is very high, the springs are very stiff and the whole polymer condenses to a point particle. So it moves classically like a point particle. When the temperature is very low, the springs are very soft. The spring is really delocalized, and you can show that the radius of the spring is more or less the de Broglie wavelength of the quantum particle. So that's why it makes sense. Okay, now you believe me maybe a little more. And you can actually sample the classical partition function of this thing using MD or MC or Monte Carlo simulations and calculate quantum thermal expectation values. This is what you need to take from this message, right? You can calculate quantum thermal averages at equilibrium from classical MD simulations of these ring polymers. That's PIMD. What happens when you have more than one particle? Well, in principle, what most people do, if you have two particles, you just replace each one by its corresponding ring polymer, okay? So you get these two ring polymers. If you want to do a water molecule simulation, then you make p copies of that water molecule, and you connect every hydrogen atom to its copy and all the replicas with this ring polymer, and every oxygen to its copy, and the other hydrogen to its copy, and so on, okay? What I would like to stress is that this is already an approximation. In order to be able to do that, you assume something very important, and that is that the particles obey Boltzmann statistics, so that they're distinguishable. Because you're going to replace each quantum particle with its own ring polymer, right? So now they're distinguishable. And this got me interested in the question of whether you could do this, something like this, that's classical like this, but not force the particles to be distinguishable. Clearly, oxygen's distinguishable for hydrogen, but you want the hydrogens to be indistinguishable. So how do you perform PIMD simulations of bosons and fermions? That was the question that got me interested in this. And the motivation, just because some people here are from physics, well, to me, good enough motivation is that quantum exchange symmetry is one of the most fundamental properties a quantum particle has. So if you want to do a method that includes quantum effects, you should probably think about indistinguishability. But if you're looking for more practical motivations, then exchange effects at finite temperature are important. For example, we're thinking about twisted bilayers and whether excitons could be thought of as bosons and could form a Bose-Einstein condensate. If you want to do a simulation like that, you have to include exchange effects, right? And why are we doing this with molecular dynamics and not Monte Carlo? Because molecular dynamics, I mean, we can give a whole talk just about this, but in brief, in principle, in molecular dynamics, you have the dynamics part. You can extract not just thermal averages, but also approximate transport properties using these approaches. So that's why we're working with molecular dynamics. Okay, so let's say you want to include this exchange symmetry in the path integral formalism. What do you need to do? In the partition function, you need to account for all permutations of identical particles. So if you have 3 particles, you're going to have 6 permutations, right? 3 factorial. And it turns out that every permutation that I've written down here below leads to a different ring polymer configuration, and which you can simply read off from what is called the cycle notation of the permutation. So for example, this is the only one you get when you assume Boltzmann statistics, but you get 5 more when you do bosons. And you might also notice that, yeah, for 3 particles, you have 6 permutations, but you only have 3 unique topologies. You have a topology where all of them are disconnected, you have a topology where all of them are connected, and you have a topology where 2 are connected and 1 is left out. So you could actually just use the unique topologies and multiply them by their degeneracy, but none of this helps, because if you try to actually do this practically, the number of permutations scales factorially with the number of particles shown here in blue. You really can't do this for anything but more than 3 or 4 particles. If you just include those unique diagrams, those unique ring polymers, that still scales exponentially with system size. That's shown here in orange. And basically, you couldn't do PIMD simulations for bosons and fermions using this approach at all for more than 3 or 4 particles. So the question is there an alternative? And the answer is yes. Otherwise, I wouldn't have been standing here and telling you about it. Let me get this out of the way. One way you could go about this that was done 30 years ago by David separately is you could try to sample the permutations. That works. But if you want to do dynamics to get approximate transport properties, there was no solution. But in 2018, we showed that you could actually do this also for dynamics exactly without any approximation, for molecular dynamics without any approximations. You don't need to enumerate all the permutations. You can actually evaluate the potential that you need to sample recursively exactly. And that's what I'm going to tell you about in a second. The first time we figured this out was in this paper in 2019. And more recently, which is most of what I'll be telling you about, we made it really efficient at quadratic scaling with Yotam last year. So, but let me tell you just how does it work? How do you evaluate it recursively? So we're going to illustrate the algorithm for 3 particles together, okay? You always start with 1 particle that has a single ring polymer that's shown up here, right? And once you want to build all the ring polymer configurations for 2 particles, you do the following thing. You go to the previous step, you take all the configurations from the previous step, and since you went back 1 step, you add to it a ring polymer of 1 particle, particle number 2. You can't go back anymore. So at the end of every interim step, you add the ring polymer of the n particles of this step connected together. Now for 3 particles, you do the same. You go back 1 step, you take all the configurations from the previous step, and you add to them a single ring polymer representing particle number 3. You go back 2 steps ago, you take all the configurations from 2 steps ago, and you add to them a ring polymer of 2 particles, particles 2 and 3, because you went back 2 steps. Can't go back any further, and at the end of every interim step, you add the ring polymer of the n particles connected together, 3 of them connected together. This is the recursive algorithm, right? And if you've been following me, you realize we got all the right topologies. You got the disconnected one, the fully connected one, and some where you have 2 connected and 1 is left out. You might think that the relative weights are incorrect, but in the recursion relation, you have a prefactor that takes care also of the relative weights. So this is how we figured out you could do this recursively. And why is this important? Because now you can prove, we showed this both analytically and numerically, that you can actually, this algorithm actually scales only cubically with the number of particles. So P is the number of beads, the number of copies of the original quantum particle that you put on your ring polymer. This is what you have to converge when you want to get the exact expectation value, right? You make them bigger and bigger until you converge to the exact result. And N is the number of particles. So this is, we've shown this analytically, numerically, this is the relative time step for 1 bosonic PIMD simulation as a function of the number of particles on a log-log scale. And if I'm right, the slope should be 3, and it is 3. So that's how this all started. And what could you do with this? So now that you could actually do PIMD simulations for for more than 3 particles, we wanted, all right, let's do the simplest boson we can think of that isn't helium, because everybody did helium before. So we started thinking about deuterium under high pressure and low temperatures. So we took solid deuterium in pressures that correspond to diamond anvil cell, I'll show you in a second, and low temperatures below 1 Kelvin. And we treated it in 3 different levels of simulation: as a classical particle, as a distinguishable quantum particle, as an indistinguishable boson, which is what we've developed. And what you do when you do these 3 kinds of simulations, no matter what's the simulation you're doing, when you calculate the structure factor, you get a solid. It's always a solid. But when you start calculating the superfluid fraction of your whole material, below it's 0 when you cool down, but below 1 Kelvin, you start getting a finite superfluid fraction. So what we figured out is that this is a sign of a quantum phase that's called a supersolid, that it has the structure of a solid, but has a non-zero superfluid fraction. So defects, for example, can flow without friction. So we made this prediction, and the pressures were a little higher than what you could do in experiments. So the experiment hasn't been done yet, but even the PRL reviewers said that they think this pressure range could actually be achieved soon. So we hope, but the experiment hasn't been done yet. So it's still a prediction. We predicted that deuterium will become a supersolid at high pressures and low temperatures. So, but I want to stress that we were very happy with this because we could do a simulation of, 128 particles in a periodic trap, in a periodic boundary conditions, but it was really hard. Those simulations took more than a year, right? So you could do this, you couldn't have done this before, but it was really hard. So then Yotam joined my group, and he did his PhD in computer science, but then got bored of computer science and wanted to do computational chemistry because computational chemistry is great. And then I gave him, when he joined the group, that paper, and I told him, read about it, and then we'll figure out the project. Came back a month later saying, it's really cool what you did during your postdoc. I said, thank you, but I can do it better. So I said, what do you mean? And he said, I can reduce the scaling from the number of beads times the numbers of particles cube to n squared plus pn. Now, this might sound like a technicality, right? At first, I thought it's a technicality, but it's technicality that matters a whole lot, because it means that the speed up you get in your simulations is proportional to the number of beads times the number of particles. So it's more important the bigger your system is, and it's more important the lower the temperature is, because P becomes larger the lower the temperature is. So actually, you get a higher speed up when it's most important. That's what I would say. So this is what you see here. You can see the speed up you get in a simulation of up to 1,000 particles. It is linear with the number of particles. And for the first time, we could actually do simulations of thousands of particles using this approach. So just give you the gist, this is my slides on what's the bottom line. And then I think I'll move on to, let's give you the bottom line. If you want to do 1,600 particles, ultra cold atoms in a 2-dimensional trap, before I did my algorithm, you couldn't do it. With my algorithm, it would take longer than 20 years. With Yotam's algorithm, it takes 9 days, right? If you want to do superfluid helium with 1,400 particles, with the cubic scaling algorithm would take longer than 14 years. With his algorithm, it takes 7 days, right? So that's not a technical matter. It's really the difference between whether you can really do thousands of atoms or you cannot. And this is the graph I'm maybe most proud of in this part of my talk. And it shows the cost of including bosonic exchange. Now, you remember, this is more or less the graph I showed you before, right? It's the time it takes to do a bosonic PMD step as a function of the number of particles on log scale, and the slope here was 3. So you got this curve. But I didn't show you the distinguishable simulation that neglects exchange effect. That scales almost linearly with the number of particles, not cubically. So the slope is 1. It's much cheaper, right? So in the past, if you wanted to include exchange for 64 particles, it would have been 100 times more expensive. If you want to do it for 1,000 particles, it would be 15,000 times more expensive. Yotam's new algorithm eliminates almost all of the added computational costs. So for 64 particles, it's only 37% more expensive to do this. And for 1,000 particles, it's just 16 times more expensive to do this. So that's what I mean by many people studied systems where exchange effects could have been important. Well, I shouldn't say maybe many, but people have studied systems where exchange effects should have been important, but were neglected because it was too expensive to do. Now I think there's no excuse. You could include it in your simulations very easily. We also develop open source software so that everybody could use this. It's still not in the development version of LAMPS just because we changed priorities. We decided instead to implement it in IPy, which is developed by Michele Ceriotti and Mariana Rossi and their former students and postdoc, and now faculty themselves. So it's implemented in the new IPy 3.0 version if you've ever used this. Super easy to use. And also the new paper describing this new version has just been accepted to JCAM Phys. So you're gonna see it very soon. Now, I've been meaning to tell you about the algorithm, but I think I'm almost in the middle point, so I should probably move to the. I'll just say very briefly. Usually, when I want to present the actual way he reduced the scaling, some people go like this, and some people go like this. So if you're the second guy, then I'm gonna skip it. So you're in luck. But the gist of the matter is that when you want to calculate this, this is the recursive relation itself. This is the potential you need to sample for n bosons, and you build it up recursively from the potentials of n-1 bosons and n-2 bosons, like I told you before, and so on. And you build it up by calculating these cycle energies, which is just k particles connected together. So E11 is the ring of one particle, E22 is the ring of one particle, in this case, particle number 1, this case, particle number 2. E12 has 2 particles, 1 and 2, and E13 has 3 particles, 1, 3, and that's the expensive bit because there's n squared cycles like that, and each one of them has at most p times n springs, so that's how you get the cubic scaling, okay? But what Yotam figured out is that in all of the cycle energies, all of the springs that are in the middle that don't connect the first and last spring, they're all the same. So you need to only calculate them once, and calculate them. There's n particles, there's p minus 1 springs, so that scales like OPN. You do this once, and then to get all of the cycles, you just extend rings with other rings. So to do the extension, you just need to break 1 bond here and create 2 bonds here. So that's an order 1 scaling because it's only 3 terms no matter how many particles you have, and you have n squared cycles. So that's how you get order n squared. So just without going into all the details, this is how you get the quadratic scaling. This is for the potential. The potential is not enough. You have to do this for the forces, but that part I'm going to skip entirely. So if you want, you can read it in our paper. So to conclude, the first part of my talk is that what we've developed, I think, is a new method for simulating condensed phase bosonic systems. Could be, I'm saying condensed phase, but it could also be dilute gases, atomic gases. That gives you the thermal averages of these systems, stuff like the Bose-Einstein condensate, superfluid fraction, and so on. You don't need to enumerate or sample any of the permutations. The latest development reduced the scaling from originally factorial scaling to quadratic scaling, which allowed us to do the first applications of really large thousands of bosonic systems using path integral molecular dynamics, and eliminates almost all the computational overhead for including exchange in PIMD. What's the next step to do what I've promised? PIMD has a lot of approximate methods to get diffusion coefficients and spectra transport properties that are much harder to get in PIMC because you have to do analytic continuation. So what we're working on right now is doing those things also for bosonic systems. So next time I'll tell you about that. Okay. All right. So before I switch gears to the other half of my talk, so we did fermionic systems. You can do the same trick you do in Monte Carlo. You do a bosonic simulation, you reweight it to get the fermionic statistics, but you get a fermionic sign problem also here, and then the fermionic sign problem eventually makes you limited to much smaller systems. So, but then we can start playing with all the usual tricks of fermionic sign problems and try to do this also here. So. More questions before I go to the other part of I prefer questions along the way, but you guys do whatever you want. Yeah. 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 So the framework doesn't care. You can do it. You just include the right permutations with the right particles. That's it. So it's actually much easier, I think, to do a mixture of distinguishable and bosons in this case. Than in what they usually do when they do, like Dominic Marx does, the hybrid PIMD, PIMC to do distinguishable and bosons. This you can do in the same framework. It doesn't care. Just do the right permutation. That's it. So we did that. That's not a problem. If you have a lot of fermions, you're going to get limited by the fermionic sign problem. But a small fermionic impurity in a bosonic bath shouldn't be a problem. Yeah. Yeah. I mean, as long as the sign problem doesn't kill you. So it's all works perfectly fine for bosons, fermions, undistinguishable.
Are you always using the same 2B for a ring for attacking?
Yeah. Yeah, you're right. It creates a sampling issue. You're allowed to do that for the right statistics, but it creates a sampling issue that we have to overcome. So what we sometimes do is we randomly shuffle the indices of the beads to overcome it. For the super solid thing, we had to do that. So that was the first time we encountered that. But yeah, we connect them at specific points, which is allowed, but hurts the sampling. So you need to do all kinds of tricks to overcome it. Yeah. In principle, you could connect and disconnect at any point along the, yeah. But we do it at a particular point for the recursion relation. So it's a sampling issue. You could do it, or you could so what they do in Monte Carlo, they randomly sample the point where you connect. So you could easily do it here as well. Yeah. Yeah. Ignore it. It's a good question. We haven't looked into it. I don't know the answer, but it's a good question. Yeah, we haven't tried to estimate at what temperature or pressure range that would make a difference in the kinetic isotope effect. So I don't know the answer, but it's worth looking into. Thank you. Yeah. Any more? All right. Thank you. So the second part of my talk, right? We're good on time. Got like 20 more minutes. And that has to do with the sampling of long time scales in molecular dynamics simulations. So nothing quantum anymore, just the classical simulations and how do you sample longer time scales. And this is the work of Aviv, like I mentioned, and John recently, a postdoc, joined my group and started working on this. It was published in these 3 papers recently. And the only reason I got interested in this is my colleague Shlomi at Tel Aviv University, who is a master of stochastic resetting. I've never heard of it beforehand. Has anyone heard about it here before? No. So I'll tell you what it is. It was really cool to hear about it. I wasn't sure we can do a lot of enhanced sampling with it, but it turned out to be really nice. So molecular dynamics simulations, like I said, are more or less limited to 1 microsecond because of the atomic time step you have to use in the integration. But many processes occur on much longer time scale. We call them rare events. The classical examples are protein folding or misfolding or denaturation, stuff like that. And what we're also interested in is the formation of molecular crystals, their growth, and also how they change shape. So what we call polymorphism in molecular crystals. They all take much too long to be sampled using standard ND. What's the usual way of overcoming the timescale bottleneck? It's a method, well, there's several of them, but one of the most popular ones is metadynamic simulations. So I'll tell you what it is. This is a standard ND simulation. I see that the GIFs are working really badly, but what you should have seen here is that the problem of long timescales comes from the fact that you have 2 states. Imagine a unfolded protein and a folded protein, or a dissolved crystal and a formed crystal, whatever you want. And they're separated by a very high free energy barrier. So if you start the much higher than the thermal fluctuations. So if you start your simulation on the left-hand side, you simply never cross the barrier to go to the other side. So that's what you should have seen here. That's standard MD. Metadynamics, what it does, if it's going to start at some point, is it asks the system every 100 steps or 500 steps where it's at, and it adds to the physical potential a small repulsive bias Gaussian potential at that particular point. So it lowers the probability you'll come back to this point in the future, right? I come from Tel Aviv, you can go to the beach with a bucket, and if you put the ball rolling in the bucket, it won't leave because the bucket's very deep. But if you fill it up with sand, that gets easier to escape the bucket, right? That's what you do with metadynamics. You fill it up with Gaussian sand grains, 100 steps, every 100 steps, one at a time. And if you do this really carefully, you could actually fill the bucket all the way to the brim, completely flatly. And then you remember from when you were a kid, you can turn over the bucket, take away the bucket, and read the imprint of the bucket on the sand, right? So that's how we can actually also extract free energy surfaces from these simulations. That's how you do it. You build the bias in a way that it converges to a uniform bias, and then you read the underlying free energy surface. What I would like to stress is that I'm a little bit cheating here because I'm showing you a one-dimensional system. But if you want to study a crystal that is forming or a protein that is folding, you have many, many degrees of freedom. And the question, which is the slowest one, becomes the most important one because you need to enhance the sampling along the slowest mode of the reaction you're interested in. And that's very hard to find, the slowest mode of the system. But if you had, we call the slowest mode the reaction coordinate or the collective variable, or CV. I'm going to use CV for the rest of my talk, okay? Collective variable. Now, if you have a good CV, which is very hard to get, you can get the free energy surface, but it really crucially depends on the quality of the CV. This is people are aware of, but what I want to stress that most people I think aren't aware of is that even if you have a good CV and you can get the free energy surface, you really bias the dynamics of the system extremely aggressively. You made it go much more faster than it would have. So usually kinetic information is much harder to obtain, right? How long would have been the rate if I haven't done the bias is much harder to obtain. So we're going to focus on that second question in my talk today. And I'm going to tell you that what I think we have a new approach to enhance sampling using stochastic resetting, and the benefits are that you don't need any collective variables. You don't need to work very hard to find the slowest degree of freedom. It's not needed. So that's a big plus. I think you can get, I know you can get kinetics inference out of it. You can infer the unbiased rate from the accelerated simulations. In fact, I would argue that it's minimally perturbative to the dynamics, as I will show you in a bit. It's super easy to implement, and you can use it also with existing methods like metadynamics. So that's what I'm going to tell you about today. But first, what is stochastic resetting? So in stochastic resetting, there are several ways of thinking about it. We're going to think of a stochastic process that has a well-defined start and a well-defined finish. We're going to call these processes first passage processes, okay? You can think the starting point, again, could be an unfolded protein, and the finishing point could be the folded native state, okay? And since it's a stochastic process, every time you repeat it, there's a different first passage time. There's a different reaction time for this transition, okay? So there's a first passage time distribution of your stochastic process, okay? What is restart? What is stochastic resetting? It means that every 100 steps or every 500 steps, while the process is progressing, you stop it and you resample an initial condition and you start it from scratch, okay? So if I have a particle who's diffusing down here and the finish point is up here, but it went to this other basin that doesn't lead to the product, I can restart it, resample the momentum, and then hopefully we'll get to the top faster, okay? That's stochastic resetting. It's very simple. But the question is, it might sound counterintuitive to why restart would actually lead to acceleration, right? Doesn't seem clear. So I'll tell you that there is a very easy criterion to check to know whether restart's going to help your stochastic process. This original first passage time distribution, right, without resetting, all you need to know is its first two moments. If this distribution has a standard deviation that's greater than its mean, it is guaranteed that introducing a little bit of resetting is going to help, okay? What's the physical intuition? If the distribution of first passage time is very wide, because I can get lost for a long time here, it's better to limit the amount of time I can spend here, restart and try again. That's why it leads to acceleration, okay? So that's stochastic resetting. Once Shlomi told me about this, I said, all right, let's see whether this works. Take two model systems. We took a parabolic trap with a Gaussian barrier, and we took this system I showed you in the previous slide, and we tailored them so that it has a mean first passage time that we can actually sample in brute force simulations, and calculated this ratio of standard deviation with the mean, which we call the coefficient of variation. And if it's larger than 1, you're guaranteed that resetting will accelerate this process. Then we did resetting, and we checked whether it actually leads to acceleration. And indeed, for this system, you can get more than an order of magnitude speed up just by doing restart. And here you can get a factor of 2. So, right, who wouldn't want to work 10 times less hard by restarting his simulations? The two colors here are two different resetting protocols. Either you come at a fixed time or at a fixed rate, okay? But they don't make much difference, as you see here. So this was nice. And then we asked ourselves, how does it work? So we took a slightly more complicated example. This is a molecule that we call alanine dipeptide. It's not the dipeptide of alanine. This is what happens when physicists name molecules. Sorry. And it has two conformers. and it does this conformational transition from this one to the other one, and it takes about a microsecond on average to go from this one to that one. And we did, 3 months worth of thousands of trajectories to calculate the coefficient of variation. It was larger than 1. This is the harmonic oscillator of the field, right? The thing you start with whenever you develop a new method. And it was larger than 1. And then we did the simulations with resetting, and it led to acceleration. But what was more important here is that we looked at the first passage time distribution without resetting in blue and with resetting in green. Without resetting, you see that it has a non-exponential behavior. It has at least a bi-exponential nature, right? There's at least 2 slopes around here. And this is why it leads to acceleration. This is a long timescale process, but not every trajectory takes forever, right? Some of them finish very quickly, but many of them take more than 4 microseconds to complete, okay? That's why it's a rare event. What resetting does, it cuts the tail of this distribution. It also, there's certain conditions at which you know for a fact that it will lead to an exponential distribution. So that's exactly what you get here. Those faster trajectories that were already going quickly towards the target, it actually makes them slower. But the long tail of the distribution becomes a lot faster because you limit the amount of time you can waste there. So that's how it leads to acceleration on average. This was all nice, but we sort of knew it was going to work once we got the coefficient of variation that was larger than 1. But then I told Shlomi, look, we have a different problem. In resetting, usually you know exactly what happens without resetting. You know what's the first passage time distribution, and you try to predict what would happen with resetting. But for our case, our field, we can't sample what happens without resetting. It takes too long. So what we did here was, a little artificial. What we want to do is we want to check what happens with resetting, accelerate the simulations, and infer the unbiased kinetics from it. Can we do that? And he said we never thought about it, so we decided to figure it out. And it turns out you can do it. There's an equation that tells you what would be the mean first passage time with resetting if you know the first passage time distribution, and in fact its Laplace transform at some resetting rate r star. So the easiest thing to do is to calculate this mean at some resetting rates and try to extrapolate to r goes to 0, okay? And you could do that. And of course, the quality of your prediction would depend on how far from 0 you started, right? What was your resetting rate? But if we wanted to do it this way, it would be totally impractical because at every point here, you have to run 10,000 simulations, right? It's completely impractical. But it turns out that using this equation, you can do simulations at some resetting rate, r star, accelerate the sampling, see what's happening, and then get all of these points for free because with resetting, you get all the short time scales included. You don't hurt them. You just don't get the long time scales. So if you do a simulation at some resetting rate, r star, you get all these points for free, and then you can extrapolate back to 0 to get the rate. Now, clearly, there's a trade-off between how big r star is and how accurate your prediction is. So you see this trade-off here. This is the speed up you get at r star as a function of the quality of the prediction, where the actual value is here. So there's a trade-off between accuracy and acceleration, but every kinetics inference method has this trade-off. But we could actually, for the first time, use this method to infer the unbiased kinetics from accelerated simulations with resetting. So that was, I think, the first paper, and it was really cute. But the problem was that resetting on its own leads, I've shown to you before, to an order of magnitude acceleration, maybe a factor 5. That's not enough. If you want to look at something that takes a millisecond, you want to look at it in a simulation that lasts only a microsecond, you need much bigger accelerations. And metadynamics leads to much bigger accelerations because you're actively forcing the system in the right direction. So, but then we realized that you could actually do resetting to any kind of stochastic process, including metadynamic simulations. So we started restarting metadynamic simulations. So this is another model system. You have 2 states on the right and on the left. You cross from the right to the left. And if you just do resetting to this system, you get an acceleration of about a factor 5, like we saw before, right? Nice, but nothing to write home about. And you also see this behavior when the resetting rate is too fast, you lose the acceleration, right? Because you don't let the particle go anywhere. It can't reach the target. But now when you do just metadynamics, here we know what the collective variable is. It's the x coordinate. It's very easy. It's a model system. You get bigger accelerations, right? You get more than, an order of magnitude more, right? This is what metadynamics typically does. It leads to faster accelerations if you know the collective variable. Now the question, what happens when you combine this with resetting? So by the way, for the blue curve, the x-axis is the bottom one. For the green and orange curves, the x-axis is the top one. So just don't be confused by it, because these are shown at the rate that led to the resetting rate that led to the fastest acceleration as a function of how fast you're depositing the Gaussians. When you combine metadynamics with resetting, you get the orange curve. What do you see here? That doing resetting either doesn't hurt you at all, or it leads to another order of magnitude acceleration on top of metadynamics. So actually, the best strategy is to do metadynamics and restart it, because it leads to either not hurting or even a 10 times more acceleration. But remember, I told you that this metadynamic simulations, they're very sensitive to the quality of your reaction coordinates. Yeah.
So the metadynamic is combined approach to go back to the very beginning every time without the additional potential?
Yeah, you have to restart also the bias, and that's a key important point. Yeah. Absolutely. You reset also the bias, everything. Metadynamics depends on the quality of the CV. So this is a model system where you can only go through an orifice here from the right-hand side to the left-hand side. It's an entropic barrier. So if you are not coming in, if you're not biasing the x direction, and we rotated the reaction coordinate artificially, the CV artificially, the acceleration by metadynamics really goes down to zero, right? Very quickly. This is what happens with metadynamics when you don't know the reaction coordinate. When you start restarting on top of it, what happened? Sorry. Okay. When you start restarting on top of it, you get the orange curve here. So what do we see here? That while metadynamics is extremely sensitive to the quality of the collective variable, adding a little bit of restarts makes you much, much less sensitive to the collective variable. So this is when we knew we had something good, because the entire community works. It is charging. It just went to sleep mode. I don't know why. It's supposed to not go to sleep mode. The entire community works extremely hard on improving collective variables, because the speed up of metadynamics crucially depends on how good you know your collective variable. What we're saying is you can get off with doing a much worse collective variable and a little bit of restart. You almost get the same acceleration as the best collective variable, right? So imagine that most of the community now trains, auto encoders and all kinds of fancy machine learning techniques to improve collective variables. You could do something much simpler, but restart your simulations and you get the same acceleration. That's what we're proposing. So just to show you that it works also not for model systems, and then I'm almost done. This is a tetrapeptide of alanine. And it has two states, an extended one and this loop structure, and two different collective variables people usually consider, phi3, psi3, and phi2. They're all dihedral angles. Phi3 is the slowest degree of freedom. So when you do metadynamics with it, you get really good acceleration. But if you don't know that it's the slowest degree of freedom, you try psi3 or phi2, you get much slower speedups because you don't know the real collective variable. What happens when you add resetting to each one of these simulations? Like before, either it doesn't hurt you or it leads to additional acceleration. And what's really cool about this is I would like to stress that for anything other than model systems, we're never in this range, I would argue. We never know the best collective variable. We're maybe at this range, so resetting will help you by another factor 5, 6, 7, or we're at this range where you have a very poor guess of the collective variable. So restarting your metadynamic simulations is almost always worth a shot, okay? And it costs nothing to do this, right? There's no force evaluation, nothing. And here is the largest system we did so far. This is a mini protein in explicit water. So it's a 6,000 atom simulation, and it folds onto itself. And there are two collective variables, one that's called RMSD and one that's called HLDA. RMSD is the simple one. It's just a root mean squared deviation from the crystal structure that you're expecting, the folded structure that you're expecting. And HLDA is some sort of not so expensive, but some sort of dimensionality reduction technique that requires sampling beforehand. So you need to do some molecular dynamics simulations, sample, and then do this dimensionality reduction, which is rather simple, but it's more expensive than just guessing the RMSD, right? And what happens when you do metadynamics with these two collective variables, with and without resetting? For the good one, as before, as a function of the bias deposition rate, either it doesn't hurt or it helps you by another 50% or something like that. It's pretty good, or another 100%. Or that's what happens for the good CV. For the bad CV, though, you can see just metadynamics doesn't do anything, right? Leads to very little acceleration. But once you add restart on top of that, you can get almost as high accelerations as you can get for the good CV, right? So just this super simple guess with no sampling and restart works almost as well as the much better collective variable. I'm not trying to advocate to not finding out good collective variables. I'm just trying that there might be a point in time where it's not worthwhile to keep going with this and just try restart and see whether that leads to the same result. So to conclude, I just want to say why I think this is a good approach. So when resetting started, it started from people considering Brownian motion, right? And what they showed, if you have Brownian motion in one dimension, then if you don't do resetting and you start at 0 and you ask how long it's going to take me to reach a point L on average, the mean first passage time diverges because it's Brownian motion. You can get lost to -infinity without reaching the target. If you reset it, it's like doing Brownian motion in a limited space, and then it becomes finite. So that's when people saw really an infinite acceleration on average, right? You go from a first moment that diverges to a first moment that is finite. And once we figured that out, we realized that actually combining resetting with enhanced sampling is a really good approach. Why? Because when you start with a rare event, you have this situation where you have two states and a really high free energy barriers to cross, okay? What metadynamics and other enhanced sampling techniques do is they try to flatten this potential out. They increase the probability of transitions, but while they do it, they also increase the probability of sampling highly improbable tails of the distribution. That's just how they work. And that's actually the situation where including resetting helps the most, right? So they flatten the free energy surface, making it more Brownian motion-like, and that's where resetting helps the most, right? Stopping you from getting lost in those tails of the distributions, which with metadynamics now have become much more probable than they should have been, right? So we actually think the best approach is to do them together. We can also it also improves the inference of kinetics from MetaD. There is a way to get the kinetics from MetaD, but it works very bad if you have very high bias deposition rates or very poor collective variables. You can get orders of magnitude error. And all I want you to take from this graph is that this is the error you get when you do metadynamics, and this is the error you get when you add resetting to it. So at every acceleration, you get much better accuracy. And the reason is what you asked, because the reason for the high errors is that you deposit too much bias before going. Once you zero the bias with resetting, it helps the kinetics inference. All right, so just to conclude this part, I've shown you, I think, a new approach for accelerating molecular dynamics simulations. We know exactly what's the condition to check for whether it accelerates or not. On its own, you can even get 10 times faster. It costs you nothing, so there's no reason not to try it. It's so easy to do. It does so by cutting the long tails of the first passage time distribution. And I would argue it's minimally perturbative because between resetting events, it does nothing to your system. So for the short time scales, you get exactly right. It's the long time scales that you cut off and that lead to these errors, to the small errors in the prediction. You can combine it with other approaches like metadynamics, and what it really does is it really lowers your sensitivity to the quality of the collective variable. So if any of you is doing molecular dynamics simulations and want to try this out, it's super easy, and it's usually either doesn't hurt or really worth your time. So I'll be happy to help you out with this. Okay, that's it. I want to thank you guys for listening and the people who did the work.